Geology and Exploration Trends in the Gulf of Mexico Superbasin in the U.S. and Mexico. Before we start today's webinar, we'd like to ask the audience a few questions about the demographics. So I'm going to launch the first question. What is your primary discipline? So it looks like we have some geoscientists on the line today. Like a high percentage of geoscientists, and over half of you have voted, and you're all geoscientists so far. So looks like we've got a very interesting audience. So the polling is continuing. So go ahead and select your discipline. And I'll go ahead and close this. So far, from the responses we had, about half of you have voted, and all of those who voted are geoscientists. So let me go share those results. It'll look pretty simple. And so now I'm going to go to the next polling question. And so our next question is, how many years of full-time experience do you have in the oil and gas industry? So here's another chance for you to tell us about your experience. We're starting to get some results in now. Okay, a few more seconds to vote on this poll. So tell us about your experience level. Less than 1 year, 1 to 10 years, 11 to 20, 21 to 30, and over 30. So I'm going to go ahead and close that. Maybe having some network difficulties. I'm going to go ahead and move to the next poll. How long have you worked in the Gulf of Mexico? So again, less than 1 year, between 1 and 10 years, 11 to 20, 21 to 30. So go ahead and tell us how much time you've worked in the Gulf of Mexico, if any. Looks like we may still be having some network difficulties. We have quite a few attendees on the webinar, but I don't see any polling results. So I'll go ahead and close this poll, and we'll move on with the introductions. So I'd like to introduce to you today Dr. John Snedden. He'll be speaking about geology and exploration trends in the Gulf of Mexico Superbasin, the U.S. and Mexico. And Dr. Snedden has worked in this field for more than 25 years. He has quite a bit of experience, including in various forms of sequence and seismic stratigraphy, sedimentology, reservoir characterization, reservoir conductivity, unconventional resource stratigraphy. He's been involved in training. He's a well-published author who's certainly written a number of well-recognized publications. Most recently, his new book, The Gulf of Mexico Sedimentary Basin Depositional Evolution and Petroleum Applications, that's just out. So we look forward to seeing more about this book. John teaches a class for SCA based in part on this book that'll be offered in April and in October in our training center in Houston, entitled The Depositional Evolution of the Gulf of Mexico Sedimentary Basin. And of course, you can contact us for more information about how to register for that course. And again, look to SCA for your training needs, for consulting, and for direct hire resources. So John, I'm going to pass the presentation.
I'm here. and start like we are just starting. Thank you guys for being patient with us. And John, go ahead.
Very good. All right, here's the agenda for today. A short introduction about why the Gulf of Mexico qualifies as superbasin. Then I'll describe briefly our tectonostratigraphic framework, which is what we also used in the book. Then I'll go into the remarkable reservoirs, both Mesozoic and Cenozoic, the special source rocks, Mesozoic and Cenozoic, the unique seals, the exceptional traps, and the amazing success stories, and finish off with some insights from the Gulf of Mexico or other basins. So a superbasin is typically defined as having remaining reserves over 5 billion barrels and past production over 5 billion barrels oil equivalent. The Gulf of Mexico easily qualifies. Estimated ultimate recovery is 200 billion barrels oil equivalent. Cumulative production is over 60 billion barrels oil equivalent. 2 or more petroleum systems or source rocks is required. Plenty of those. Stacked reservoirs, as you'll see, many of those. And importantly, as shown on your right, a whole series of infrastructure and market access connections. 52,000 wells, 7,000 platforms in the northern GOM, and a well-established pipeline system in Mexico, including 2 offshore areas. In fact, you might consider the northern Gulf of Mexico, onshore and offshore, to be its own superbasin, with Mexico, Sureste, Tampico-Misantla being another. The U.S. Gulf of Mexico represents about 50% of the ultimate technically recoverable resources, about 74 billion barrels oil equivalent. That's about half of the U.S. UTTRR. Mexico, 13 billion. Numbers might be a little high. So this is the location of the Cenozoic and Mesozoic fields in the US, Mexico, and Cuba. The distribution actually makes good geologic sense. As you can see here, there's a dashed line. Outside of that dashed line are primarily Mesozoic fields and discoveries, both oil, green, and gas, shown in red. Inside of that dashed line, we have primarily siliciclastic systems in the Gulf of Mexico basin. The reason for that dividing line is essentially that's a change in crustal type, where we go from continental to transitional crusts. The carbonate systems that dominate the Mesozoic prograde to that point were unable to prograde any further because of the high accommodation on transitional crust. Water depths got great, and essentially you ended up outside the photic zone, which carbonates love. Siliciclastics, by contrast, don't care. They prograde past that margin to the present day position, located about this position here in the northern Gulf of Mexico. Now, notice also in this slide, there's a tremendous amount of white space that is the zone of future exploration. We've divided up the stratigraphy of the Gulf of Mexico into really 6 tectonostratigraphic phases. Starting at the base, following the end of the Ouachita Marathon orogeny about 300 million years ago, a long phase of crustal attenuation, rifting, and successor basin fill that ends about the point the first stage of oceanic crust is formed. Full-on oceanic crust begins around 170 MA, initiating the drift and cooling phase, and that goes on to about 140 MA. That's where seafloor spreading shifts to the Caribbean. Then we have a period of time of what we call local tectonic and crustal heating, essentially fixed points on a fixed crust that causes local uplifts and unconformities. That Mesozoic phase ends at 66 MA with the Chicxulub impact. And then we have 3 Cenozoic tectonostratigraphic phases: the Paleogene Laramide phase, Middle Cenozoic geothermal phase, and the Late Neogene tectonoclimatic phase, all phases that represent what's going on in the hinterland. that generates so much siliciclastics that is deposited in the basin. Bottom line of this diagram is virtually every stratigraphic unit in the US-Mexico area has reservoirs in this interval producing somewhere. If we look at the stratigraphy of the producing reservoirs in the offshore federal waters, it ranges from Pleistocene all the way to Upper Jurassic. This diagram represents the UTRR, million barrels oil equivalent. In black are the number of fields or discoveries that make up that total, and gray shows the UTRR. The largest by far is the Paleogene Wilcox, about 26 discoveries in fields, 21 billion barrels, primarily in the subsalt domain. The Mesozoic has less. However, the Upper Jurassic Norphlet play is the newest, 20 discoveries or fields, about 5 billion barrels oil equivalent, including the giant Appomattox field in the northern Gulf of Mexico. Shale has continued its success with discoveries at Rydberg, Dover, and the Chevron operated Ballymore discovery. There's about 20 valid tests over a 15-year period with a 55% success ratio of wells finding live oil above a geominimum. That's kind of at the high end of your global average. So let's talk a little bit about that Norphlet. It's kind of special. This is our reconstruction, accounting for both seafloor spreading as well as rafting. We have a fairly narrow Gulf of Mexico basin. It's much smaller than it is today. On the northeast corner, we have an Aeolian sand sea or erg system. Aeolian sands deposited under arid conditions. These transition seaward to a Sabkha deposit and a shallow marine seaway. And to the east, they transition to fluvial wadi deposits. A very large area of exposed basement that loose terrigenous sediment is blown by the wind into this erg. We believe a smaller erg exists in Mexico, down here in Yucatan. Together, these represent one of the largest Aeolian deposits in geological history. Let's zoom in now to this area of the middle ground arch. In this area, it's very complicated from a structural standpoint. Blocks of Smackover and Norphlet have, following deposition, rafted westward and southward. Their original position is shown by the reddish color, and their present day position is shown by the yellow. So for example, blocks like Ballymore and Appomattox have moved something on the order of 40 to 50 kilometers to the south and west. So not only do you have to reconstruct for plate tectonics, but also for salt rafting. On your right is an example of Aeolian crossbedding from these Norphlet sandstones, high angle crossbedding, generally unimodal. You can see on your far right, ultraviolet light indicating the presence of oil. And then in the lower diagram below the oil water contact, you can see the natural reddish color of those Aeolian sandstones. Important reservoir types beyond just the Aeolian sandstones. In Mexico, we have important deepwater breccias, carbonate breccias that aided by exposure, dolomitization, and fracture generation during the Middle Miocene Chiapas orogeny, develop a unique triple porosity system. This is the largest producing interval in Mexico. In the Wilcox, these Cenozoic sandstones, we have deepwater deposits, dilute turbidity flows, what's known as the Bama succession TA, TB, TC, and repeat TB, TD, and E. In Mexico, our Miocene sandstones slightly coarser grained because our orogenic belt is very close to our basin margin. So I'm going to run through quickly a movie of the Cenozoic deposition in the Gulf of Mexico basin, and you can see some very important features. First, As we go through the video, you'll see the development of very large submarine fans in the northern Gulf of Mexico. These are linked to long run-out channel systems that go all the way to the northern and middle Rockies. In Mexico, because the orogenic belt is closer to the basin, we see smaller fans coming through, in some cases, canyons like Chicantepec and Bajuco. Late in the video, you'll see the development of the Tennessee River system that's linked to rejuvenation of the Appalachians. This triggers new fans in the eastern Gulf of Mexico that are 1 billion barrel oil equivalent discoveries. And then finally, we'll see the impact of that middle Miocene Pacific plate tectonics affecting Sureste, Chiapas, and submarine fans down in the Veracruz Trough. So let's start the video. Just kind of get my video to show up. Well, we'll bypass that video for now, come back to it. If you look at the top 10 wells that produce in the northern Gulf of Mexico, today they are located all in the deep water. These wells have a daily production rates ranging from 11,000 barrels a day to 15,000 barrels a day. Compare that to an average onshore Austin Chalk well of 300 barrels a day. Considerable difference. Most of these are Pliocene reservoirs. We have 2 Paleogene producers, Chinook and St. Malo. In terms of cumulative production, again, all these wells are located in the northern Gulf of Mexico in 3 protraction blocks: Green Canyon, Mississippi Canyon, Walker Ridge protraction blocks. All are Pliocene, Mars Field, Tahiti, Thunder Horse, and then the excellent porosity and permeability has a lot to do with those cumulative production rates. Some well slots are actually approaching 100 million barrels. That's essentially 15,000 barrels a day production from a single well over 20 years. In Mexico, the major reservoirs are largely Mesozoic carbonates. There are exceptions to that: the Ekbalam area, Oxfordian sandstones near Cantarell, recent discoveries at Hazama and Trion, which are under development, then a long history of production in Cenozoic sandstones of the Veracruz Basin and the Burgos Basin. These carbonate reservoirs were deposited in a variety of depositional, structural, and diagenetic settings, ranging from those KPG deep water breccias I mentioned, Middle Cretaceous platform margin reefs and slope aprons, and surprisingly, the second best producer in Mexico is actually Upper Jurassic grainstone banks. These have a wide range of macro, micro, and fracture porosity types and produce over a considerable depth range, down to over 6 kilometers in a recent discovery by Pemex. Now let's talk about those world-class source rocks. We had access in our project to reservoir oil and seep data from GeoMark, one of our partners, and this has allowed us a window into understanding our source rocks. In fact, if the Gulf of Mexico was a frontier basin today, those seafloor seeps and reservoir oils would signal to you that you have 2 world-class source rocks. So let's talk about those: the Tethonian centered source rock and our Cenoturonian source rock. Cretaceous oils, Cenoturonian source, are very well known in the central Gulf of Mexico. You can see here in this cross section on your right, wells like Norton have TOCs, total organic carbon contents, of about 4.3% TOC. It declines slightly toward the Tiber well, down to 2%, primarily we believe due to dilution by this deepwater submarine fan system. and then tapers off to the west. Of course, onshore, we have a world-class unconventional play, which is the Eagle Ford, as shown here in Texas. You can see we have an extension of that into Louisiana known as the Tuscaloosa Marine Shale. Turns out these are slightly different in age, with the Eagle Ford being older, below the oceanic anoxic event 2, whereas Tuscaloosa Marine Shale, by our work, is younger than that. You can see the total organic carbon content determined by using delta log R. Tectonic center-sourced oils, probably the richest source rock overall. It's important both in the northern Gulf of Mexico, particularly in the central Gulf of Mexico, but as well down in Mexico, the Pimienta source rock, where TOCs in places can be as high as 7% total organic carbon and thicknesses above 1,000 feet, very common. Of course, onshore, we have a world-class unconventional reservoir in the Haynesville and Bossier shales, although due to the depth of burial, they're more gas prone than the Central offshore. It's also important to talk about the effects of the salt canopy in kind of mitigating heat flow. Salt acts to conduct heat and will tend to cool the strata underneath it. We clearly see that. On your left in that diagram, we have shallow oil and gas windows for the Jurassic and Cretaceous in the East Texas Basin. When we move offshore, we see there's a progressive drop in the oil and gas windows underneath salt, again, due to the mitigating effects of that salt. So this keeps our Mesozoic source rocks generating later and longer than you would have observed onshore. So it's very possible to get oil discoveries down dip of gas. What about the seal rocks? We're blessed in the Gulf of Mexico to have excellent seal rocks. All those organic rich intervals that I described, Tethonian, Cenoturonian, and the Oxfordian, are effective top seals within the Mesozoic in the northern Gulf of Mexico. We also have proven upper Eocene and shales around the PETM, the Paleocene Eocene thermal maximum. They seal the Wilcox. We have proven neogene seals and salt that hold very large columns, even at very high dips. This diagram on your left shows the Heidelberg field with very steep dips around that weld. In Mexico, similar, Tethonian shales top seal the Campeche reservoirs, and as shown in the diagram, we have Paleocene shales that top seal KPG reservoirs, as shown in the Cantarell field area. Both duplexes are top sealed by Paleocene seals. We have largely unproven neogene seals, and there has been some concern about those seals, as I'll describe, but we also need to keep in mind the possibility of trap timing issues, which might be more relevant here. What's that based on? A few years ago, some drilling was done by Pemex, drilling 2 wells, Kuna and Yoka, and somewhat to their surprise, these very large traps were clearly underfilled. Underfilled at Kuna and largely wet at Yoka. And that raised some concerns about the upper Miocene seal rocks. We had, as part of a master's thesis study, tested those seal rocks and determined that the top seals are actually pretty good. So the issue isn't the quality of the top seal rocks, but it's really an issue around trap timing. If you reconstruct the history of trap development here at Kuna, as shown in the lower diagram, we really don't see significant trap volume developed until well late in the Miocene, and really the peak is in the Pliocene. Unfortunately, that trap timing is later than the transformation of organic material in key source rocks, Tethonian, late Cretaceous, even the Wilcox for that matter. So we have an issue of trap timing relative to migration. Still have very good seal rocks. If we can find the right appropriate trap timing, I think you're in much better shape. What about traps themselves? Well, we have both in the south and in the north, a great diversity of proven and prospective trap types, and of course, related success stories. In the northern Gulf of Mexico, Paul Weimer has put together a nice classification scheme of the trap types. He's divided up the northern GOM into 4 tectonic provinces. To the north, the Basins province, which includes many of the bucket weld systems, the inboard Wilcox of Green Canyon, Garden Banks. To the south, the more outboard Wilcox arena, we have the subsalt province, which has its own set of challenges, particularly due to salt imaging. Further offshore, Keithley Canyon, Walker Fold Belt, Mrs. Canyon Fold Belt, and Perdido Fold Belt. And then seaward of the salt canopy, the abyssal plain. So if you look at the different trap types that are present here, you'll be impressed by the considerable diversity. You have salt cored folds, such as at St. Malo, remigration traps, fault-dependent closures, such as at Hadrian, salt cutoff traps, like at Vito, attics below salt, turtle structures, such as at Thunder Horse, low relief anticlines, like at Tiber, even weird stuff, like encapsulated mini basins completely surrounded by salt. And then in that Basins province, 3-way bucket traps. Here's an example of a turtle structure, the BP operated Thunder Horse field. You can see the over thickened lower Miocene section shown in the pinkish color. It's clearly an inverted high. That is, originally it was a basin, which explains why it's over thickened. And that basin with salt withdrawal into the allochthonous salt zone inverted, actually flipped. And so the basinal low becomes a structural high. And that's true also for the middle Miocene. Billion Barrel Field. Another trap type that's important in the northern Gulf of Mexico is the Atlantis structure, salt cored fold. Reservoirs here are primarily middle Miocene deepwater submarine fan deposits. Very high porosity, 26 to 32% at 20,000 feet drilling depth, and permeability is over a Darcy. Reservoirs are extremely high net to gross, very high quartz content, very little clay or cement. However, in spite of this sheet-like distribution, we do have reservoir compartmentalization issues. Localized development of deformation bands and subseismic faults have induced considerable reservoir compartmentalization. So don't assume that a deepwater sheet sand has no compartments. The prize in Mexico is clearly the Salina de Zamora Campeche salt basin. It's relatively lightly drilled. Very few wells drilled in this area. It's a complicated area, as you'll see. Key wells to mention, Tamha, then I mentioned Yoka and Kuna on the flank of the system, Lacme to the south. A recent 72,000 square kilometer 3D wide azimuth survey shot by Western GECO has demonstrated that there's an abundance of trap types, from salt cored folds in the north, tight folds and thrusts in the south, thrust and local salt tectonics in the middle, and abundant salt basins, as you'll see. So here's the diversity of trap types. It differs significantly from the northern Gulf of Mexico because of the superimposed shortening related to the Chiapas unconformed orogeny. You have your standard turtle structures, but these are a bit squeezed. Salt cored folds, but what is unique to this basin is things like thrust weld feeders, squeezed vertical feeders, pop-up feeders, thrusted anticlines, and even shale detachment structures. So a different diversity of trap types. Of course, we should mention the Hazama discovery made in 2017 by Talos and partners. A relatively simple trap is shown on your left, 3-way upthrown trap with a very prominent flat spot. You can see that on both the amplitude map and this cross section, which I took from the Premier Oil website and superimposed in a master's thesis from Mexico. The trap is a relatively simple closure, and it's estimated that with an oil column of about 1,000 feet, 340 meters, there's about 670 million barrels recoverable. Finally, I would like to mention another important success story, which is the success of the seismic industry in improving imaging over many of these subsalt fields. The example I show here is the Mad Dog field in the Gulf of Mexico. On your left is a 1998 narrow azimuth survey. Because when you shoot a narrow azimuth survey, most of the recorded signal is essentially traveling parallel to the sail line at a very small azimuth. And since you're illuminating your target in really just one direction, you really have a hard time making out complicated imaging below salt. You have multiples to deal with. Industry adapted to that by shooting wide azimuth data designed to widen that azimuth distribution over the target. Each source line is shot multiple times with increasing lateral offset, so you get a significant uplift in illumination and suppression of multiples. It's really quite remarkable what industry is able to do. And of course, a lot of advances since 2005, tilted transverse isotropy and full waveform reversion, and it's just amazing what you see today. Here's an example published by Leyendecker et al. Showing imaging below salt in the northern Gulf of Mexico. You must be impressed by what you can see below the salt canopy. You can trace individual seismic reflections for a great distance. You can see the salt ascension zones. You can see the weld structures and the salt cutoff traps, Pliocene, Miocene, and so on. Imaging below salt is just as good as above salt. So to sort of wrap this up and allow time for questions, here's a few lessons from the Gulf of Mexico Superbasin. First, around salt, expect the unexpected. You see mitigation of heat flow, and thus your older source rocks are viable much longer. And of course, the salt canopy hides important salt traps that might harbor large discoveries. There is a variety of trap types, providing multiple exploration opportunities, both in the northern Gulf of Mexico and in the southern Gulf of Mexico. Had I a chance to show you the video, I think what I've demonstrated to you the mountain belts and their linked drainage systems, how they rise and fall, and sometimes they rejuvenate, in the case of the Appalachian Tennessee system. In the Gulf of Mexico, we're blessed by multiple working source rocks that ensures that migration shadows and underfilled traps will be quite rare. And reservoir characteristics may vary, even at deep water sheet sands, as we showed in the case of the Atlantis field, Middle Miocene. And then finally, never underestimate the ability of our industry to make technology improvements that will greatly enhance seismic imaging, drilling, and hydrocarbon production. Thank you very much. The book, as was mentioned earlier, will be provided with the course we give in April. And at this point, I think it might be useful to take some questions.
Okay.
Great, John. Thanks very much. I want to remind our listeners today that you are muted, but you can ask questions using the feature in the GoToWebinar question panel. So if you'll type in your questions, I will read them, and you will be anonymous as we read them. I have a question, John, just to get things started. You talked a little bit about the 20 valid tests in the Gulf of Mexico and some 15 years recently that had a 55% chance of recovering live oil above a geo minimum. What do you think accounts for that unusual high chance of success?
Well, it is at the high end of the global range. It's not like an outlier, but I think this is an area where industry has spent a lot of time acquiring wide azimuth seismic data mapping off of 3D seismic data, and they've greatly improved the imaging in and around the traps. Of course, with successive drilling campaigns, you better understand the trap. I think a really interesting story about that play is encapsulated in Ted Godo's paper in both 2018 and 2019. He wrote 2 papers that illustrates the persistence that Shale had in pursuing this play in the Northlet. And by each successive dry hole, they progressively reduced their risk to the point that now there is just one discovery after another.
So persistence matters, huh?
It does.
Great. So you also mentioned that in the case of the Gulf of Mexico, the trap timing was as important as the quality of the seal rock. So tell us a little bit more about that, making sure that you have the trap before the migration.
Yes, and this issue, which was raised in Mexico primarily, is also one that we do occasionally observe in the northern Gulf of Mexico, where the traps, due to salt tectonics or other processes, will form quite late. In the best example in northern Gulf of Mexico is the famous Destin Dome north of Florida. Salt withdrawal and the formation of large salt structures really occurred post-Miocene, well after migration of hydrocarbons. So even though you have a lot of large traps, you don't necessarily have a charge because the trap wasn't there when the oil migrated from the source rock. In Mexico, it's known that as we move westward toward the Veracruz Trough in the saline in the Campeche Salt Basin, that the traps are progressively younging. So we have to rely increasingly upon younger and younger source rocks that are available to generate later. Early source rock maturation in migration when the trap's not available is generally a fatal flaw. But don't assume that underfilled traps are entirely due to seal failure. Many of the seals we tested in Mexico are actually pretty good.
Great. And you also talked about the importance of source rock and the equivalencies on shore with the Eagle Ford and the Tuscaloosa Marine Shale and the Haynesville and the Bossier. Are there any other learnings that you can draw from your studies of the Gulf of Mexico that might help those who are working in the unconventionals onshore?
Well, of course, the unconventional realm is a little different than the conventional realm that I've been speaking of. We're not doing unconventional offshore, but we have studied the unconventional plays, and the obvious thing is to find the richest organic material, but also some of the concepts from the conventional world apply. So as a great example, EOG in developing the Eagle Ford in the Karnes Trough area focused in on a place where they could find the Eagle Ford equivalent in the oil and gas window, not over mature, not under mature, but where it was generating, so that we could flow from those microporous systems. So basin modeling played a big role in their success in the Karnes Trough of Karnes County, Texas. In other places, we have to be careful of things like water cut. The Austin Chalk trend in onshore areas of Texas and Louisiana can have a very high water cut. And the problem there being the fact that we have late faulting that brings water upward from deep saline reservoirs into our source rock interval that we're trying to produce from. So there are some factors that are unique, but it's still the same drivers. The presence of high TOC intervals within the oil and gas window, and with enough continuity that you can make long reach drilling really work.
Okay. We're receiving some requests for the video, again, from our listeners. Do you want to give that a try one more time now that we're near the end of our session?
Yep. So I'm going to go backward.
Great.
Now, if I was to take it out of side presentation mode, would that be an issue?
You can sure try that. Let's see if that works.
Ah, there you go. All right. It showed up. All right, so here we go. And I'm going to do this a little quicker. All right. So big lower Wilcox fans. And then middle Wilcox time is really the acme, the longest fans that we see in the basin itself, because the orogeny in northern areas is quite large. Down in Mexico, we still have fans coming out of the Chicontepec Trough. By the time we get to upper Wilcox time, we're starting to see a retrogradation of the fans in the northern Gulf of Mexico due to two factors: climatic change in the source terrain, but also we have a large raft zone in South Texas. We do see expansion of the fans in Mexico, particularly fan systems coming through the Veracruz Trough. And then by Queen City time, upper Eocene time, the fans have really shut off in the northern Gulf of Mexico. A couple of reasons for that. Again, climate change in the Rockies. We also have it's a global sea level high stand phase. We do have fan moving, still continuing to prograde down the Veracruz Trough, and we see fans at Pachuco and Chicontepec. That pattern continues in the Yewa time, with which just a lot of sand stored in deltas and shore zones. And then in Oligocene Frio time, the initiation of the Rio Grande Rift, as well as a lot of sediment coming down the Paleo Rio Grande system, gives us a large amount of sand coming into South Texas, unfortunately trapped in the Vicksburg detachment zone. A separate river system we call the Rio Bravo is actually the one that we think is most important to Mexico into the Salino de Bravo, the Norias Delta system. The Norma conglomerate is quite coarse, suggesting we're very close to our source terrain. Moving now into the lower Miocene time, we're still continuing to funnel sediment through the Veracruz Trough. In the northern GOM, we have the first indications of a small, narrow submarine fan system in Mississippi Canyon. That continues until we start seeing elongate fans on the east side of the basin, suggesting that we're getting some contribution from the Appalachians, the rejuvenated Appalachian. Still continuing large amounts of sand coming through the Veracruz Trough. And now, in middle Miocene time, the full-on Tennessee River system, due to rejuvenation of the Cumberland Plateau, we develop a large-scale fan system in middle Miocene. That is the Thunder Horse fan. We continue that pattern into the middle Miocene, upper Miocene, excuse me, and we're starting to see the fan consolidate in the east, but also diversion of discharge going out to the west. Continuing some sedimentation in Mexico down the Veracruz Trough, but also sedimentation coming into the shallower water areas, Hazama, and so on. By Pliocene time, competition between the Mississippi River, Red River, and Tennessee is ongoing. And of course, by stealing catchment, eventually the Mississippi wins that battle. That's apparent in the next episode, where the Mississippi River has grabbed the catchment of the Tennessee and developed in the eastern part of the basin a huge submarine fan that covers almost half the basin. That combined with the Bryant and the Almeidas fan. We have an apron down in Mexico at this point, filling in mini basins in the south. And to finish off, here's the distribution of all these fans in the basin from top Cretaceous to Pleistocene All these fan systems are attempting to fill this big deep hole we call the Gulf of Mexico Basin, but they're unsuccessful because we're still in abyssal plain water depths out here. So thank you very much.
Thanks, John. That was truly remarkable, that highlight of your presentation. We have one more question from a listener. What might be the cause of large underfilled structures traps, such as Tiber?
Well, there could be a variety of causes of underfilled traps. Generally, we don't ascribe that in the Gulf of Mexico to source rock efficiency, but there could be unknown spill points. Some seal rock failure is possible. Also, there's a possibility of the routing from the source rock through pathways that maybe you're not collecting to go into an individual structure. So the specific case of Tiber, it does have oil and gas in the Wilcox and in the Cretaceous section, the Tuscaloosa equivalent, but is at the Tuscaloosa level challenged by porosity and permeability issues. It is also possible, as we saw in the Norphlet case, that if your reservoir has poorly developed porosity and permeability, at the time of migration, you might not get much in there. And that is clearly a case that we see in many of the Norphlet failures in the eastern. So it's possible that at the Tuscaloosa level, maybe that's what's going on.
Thank you. I'd like to thank our listeners for attending today's webinar, and we especially appreciate your patience as we worked out our connectivity problems. Later today, you will receive a link to a recording of today's webinar. You'll also get an evaluation form and a link to register for Dr. Snedden's class entitled Depositional Evolution of the Gulf of Mexico Sedimentary Basin. That's scheduled to be taught in Houston in April 27th through 29th, and